Okay, two skaters with masses m1 and m2 push off each other and travel in opposite directions on a frictionless surface. If they do a total work of w during their push, how fast is each skater going? Okay, so this is kind of interesting. It's an interesting twist, right? So we have skaters pushing off each other. So we want to think about a momentum first of all. So before they're just sitting here, and afterwards, then this guy goes off with v2, this guy goes off with v1. Okay. So what we know is that before, if we just talk about the skaters pushing on each other on a frictionless surface here, when they push off each other, okay, before they finish doing the pushing at all, their velocity is 0. So that means their momentum before they push off each other is 0. And the momentum after they push off each other, let's say v2, let's say to the right is positive, is negative m1 v1 plus m2 v2. Okay, so we're going to say that, and then how do we know momentum is conserved? Is because if we're on a frictionless surface, there's no external forces while they're pushing on here, no other external horizontal forces, then there's no change in momentum, right? So then you know that 0 equals the negative m1 v1 plus m2 v2. You know the momentum before and after now match. Okay, so that's the first part. Now, here's the part. They do work during their push. Now, what is their work doing? Their work on each other has to be causing a change in energy in their system. And their system is definitely changing energy. As they push on each other, they're changing each other's energy, right? Of the system. And that's because right now, before they push off each other, they have no kinetic energy. And afterwards, they have some kinetic energy. How much kinetic energy do they have afterwards? Well, that's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Kinetic energy is positive. You could technically put negative v1 squared, but if you square it, it just becomes positive anyway. Okay, and this kinetic energy must have come from the work that they did to push off each other, right? That's where they got the speed from. That's how they are moving at all. Okay, so W is a known quantity. Now, so I have two equations and two unknowns. What I don't know is v1 and v2, and I want to solve them. So what's the easiest way to do this one is maybe I'll solve for v2, for example. v2, well, so moving this equation, I'd get m1 v1 is equal to m2 v2. Just moving the m1 v1 to the other side. And then v2 is equal to m1 v1 over m2. And we can plug that into there to solve for v1. So I'd have 1/2 m1 v1 squared plus 1/2 m2 times m1 v1 over m2 squared equals w. Okay, this is 1/2 m1 v1 squared plus 1/2 m2, and this is m1 squared v1 squared over m2 squared. Just square everything. One of these m2s are going to cancel like that. And so now I'm going to have, I can pull out a v1 squared on both of these. I can pull out a 1/2 also. So if I pull out a 1/2 v1 squared, this guy just has m1. If I pull out a 1/2 and a v1 squared, this one has m1 squared over m2. Okay. I could factor out another m1 if I wanted to, but I don't know. It's not a huge deal on how you want to if you want to factor that part, but let's just solve for v1. So I'm going to multiply by 2. And then divide by this quantity to get v1 squared. Oops. m1 squared over m2. And then finally for the v1, I'm going to get the square root of this. Okay. Awesome. So that's what the first guy is doing. It's in terms of W, M1, and M2. Now V2 is M1 over M2 times V1. So V2, you just simply do M2 over M1 times V1. M2 over M1 times the square root of 2W over M1 squared plus M1 squared over M2. Okay. Now you could do, you probably could do some pulling out of M1 and M2, but it's really not that big a deal. We'll just leave it at that. There's some simplifications you could do probably to make those quantities a little bit better, but that's pretty much it. We use the energy, the work in energy, and conservation of momentum.